VdP plus sigma Ni d mu I is equal to 0. This is a fabulous equation. This is a fabulous equation. It's the beginning of chemical thermodynamics. It looks simple. It is not. It's a big philosophical equation. I am erasing this. It's not necessary anymore. This equation is called Gibbs-Duhem equation. It's called the Gibbs-Duhem equation. SdT minus VdP plus sigma Ni d mu I. Now, at isothermal isobaric condition means what? At isothermal isobaric condition means what? That means T is a constant because it's known. You have said that T is known. Therefore, dT is equal to 0. And P is also constant. Therefore, dP is equal to 0. If you apply this at isothermal isobaric condition, sigma Ni d mu I is equal to 0. Tell me, have you understood? This is important. No, you can't tell me. Okay, right. So, this is Gibbs-Duhem equation, right? Let's say this says the derivative of T, derivative of what are the variables? Let's say this is dt, dp, and d mu I. These are all the variables that you have. All the variables that you have. What does it relate to? A particular phase. The number of variables in a particular phase. That means it is the number of variables means what? Means the pressure, temperature, condition it is subjected. And the other variables. What are the other variables? The other variables are the mole fractions of the different components and mole fractions means moles Ni, the number of moles of different components in the phase, and the free energies of those components in the phase. Say, for example, have you understood? What are the variables? dP, dt, Ni. What is Ni? The number of moles of phase component in a phase. What is mu I? Is the chemical potential. Remember, G by N is it's also a free energy term. Well, it's also a free energy term, which is the free energy of the different components. So this equation connects all the variables that is affecting the stability of the phase. All the variables, temperature, pressure, the moles or the mole fractions, and the free energies of the different components. It's all linking them into one equation. At isothermal isobaric conditions, that's a known pressure temperature condition. That means T is constant, it's known. P is known. That means dt by dP is equal to 0. Then it says Ni d mu I is equal to 0. What does this mean? So now temperature pressures are not the variables because isothermal isobaric means pressure temperature conditions are known. They are known now. So they are known. So the derivatives are 0. So this links the moles and the free energies of the different components in a phase. Let me tell it easily. olivine is the phase, and there are two phase components, forsterite and firelite. So what does this Gibbs-Duhem equation do for olivine at isothermal isobaric conditions? Okay, let me write it for the full and then I will write it for this. Okay. So for olivine, if I write this Gibbs-Duhem equation, it will look like S olivine dt minus volume of olivine dP plus, now you see, N of forsterite in olivine into d mu of forsterite in olivine plus N into firelite in olivine into d mu firelite in olivine. This is how it looks like. The Gibbs-Duhem equation of an olivine would look like this. If olivine also contains manganese, which it does normally, normally contains manganese, then you will have another component of manganese. So these are your variables. These are all your variables in olivine, and the Gibbs-Duhem equation links all it into one platform. Now at isothermal isobaric conditions, dt will be equal to 0, dp will be equal to 0. So if you take this, it will be N forsterite in olivine into d mu forsterite in olivine is equal to, plus N firelite in olivine plus d mu firelite in olivine, and this is equal to 0. I have forgotten the 0. I forgot to write the 0 here. So this is what happens for olivine at isothermal isobaric conditions. This is what happens for isothermal isobaric conditions for a simple binary solid solution. Now, if I bring this here down and write N forsterite in olivine is equal to then minus d mu firelite by d mu forsterite in olivine into in firelite. Now look at this. What does this tell you? Now you see here, I was here for not an isothermal isobaric condition. Then I change this to isothermal isobaric conditions, and now I write this expression. What does this expression tell you? It tells you a very important thing. It tells you that if you happen to change the number of moles of forsterite or X forsterite, say for example, or for example, if you know N forsterite and you know what is X forsterite? X forsterite is equal to N forsterite divided by N forsterite plus N firelite, right? So that is olivine, that's olivine, that's olivine, and that's olivine. So X forsterite is nothing but N forsterite divided by N forsterite plus firelite. Now you see here, so it's a very interesting thing. If you happen to change this, even at isothermal isobaric conditions, this will change. This has to change because this does not change. This does not change because this, for a pure phase, it becomes a constant ratio. So if you change this, one components, the other components need to change, but they should add up. They should be here. N phosphorite plus N firelight, this has to change. So if you want to change N phosphorite because of something, then you need to change N firelight. That means all these variables in this equation are not independent variables. There are independent as well as dependent variables. There are independent variables and dependent variables. Say, for example, x plus y, x plus 5y is equal to 5. Now you see, if you put a value of x, independent variable, if you take a value of x, y is automatically fixed. Have you understood? If you change x, y will have to change. So x is the independent variable, y is the dependent variable. Look at here. If you want to change this, if you want to keep it at a particular value, this is fixed. This is fixed. But if you want to change this, this has to change. This has to change. Now that is very important to tell you that Gibbs-Duhem equation, essentially what it does, it links all the variables, including temperature, pressure, and the different modes, into one single equation. But all the variables here are not independent variables. There are also dependent variables. Just like x plus 5y, if you put x is equal to 2, then y will have a fixed value. Y becomes a dependent variable. You can't change, if this equation is true, you can't change both x and y arbitrarily. It fixes according to the equation. Similarly here, if you change phosphorite, firelight will not change arbitrarily. It cannot change. It's fixed by this reaction, by this equation. You can't change it arbitrarily. So one, if it becomes an independent variable, other becomes an independent variable. It has to change as controlled by the particular equation. So, this is one important thing about phase components, and between phases and phase components. A phase can be written in part, as always, by a Gibbs-Duhem equation. In a Gibbs-Duhem equation, the variables are temperature and pressure, as well as the phase, as well as the number of moles. Have you understood? So, but all of these variables are not independent variables. There is independent and dependent variables. So all of them are not independent. You don't need to quantify all variables. One of the other two variables will always be dependent. Right. So the accompanied write-up that I have given you for the derivation of Gibbs phase rule essentially depends strongly on Gibbs-Duhem equation, although it's not said. But now if you read that particular write-up that I will give you, you will see that this is a very important equation that they use. Chemical potential, Gibbs-Duhem equation, and mole fraction. Remember, in a mole fraction, say for example, in this equation, x phosphorite, if you find out a particular way of x phosphorite, then x firelight itself becomes a derivative, becomes a dependent variable. Because x phosphorite plus x firelight is equal to 1. So if you change 1, your order is automatically fixed. These two terms, Gibbs-Duhem equation and mole fraction equations, are intertwined in finding out the Gibbs-Duhem in terms of the Gibbs phase rule. In the next class, we will talk about Gibbs phase rule. We'll start with Gibbs phase rule. But before that, before to end this class, I will just try and introduce you. We have talked about what is called a system. What is called a system? We have talked about a phase, and we have talked about phase components, and we have talked about how phase and phase components phase components and other variables are integrated into the Gibbs-Duhem equation, we are left with one important thing. It's called components. When said this way, components are two. One is called a phase component and the other one is called a system component. A phase component describes the chemical variability of a phase in a system. Or a phase component describes the chemical variability of a mineral in a rock. But when you talk about system component, then you need not to talk about only one mineral, but the whole rock, which could be multi-mineralic. So that is what is called a system component. So when somebody says component, it essentially means system component. It essentially means system component. Otherwise, the right way is to say system components and phase components. They mean completely different things. Now say, for example, what is a system component? Now, the ideal definition is the minimum number of molecules or minimum number of molecules or components of a system. Chemical variability of a system. It is the minimum number of components that describe the chemical variability of the system, or minimum number of formulae that describes the chemical variability of a system. That is what is a system component. Now let me explain. Say I have a mineral Al2SiO5. I can write it as 2Al plus 1Si plus 5 oxygen. I can write it. Or I can write it as 1 Al2O3 plus 1 SiO2. Or I can write 1 Al2SiO5. This I can express in the three ways. If here I write it this way, I require three formulae. If I do it this way, I need two formulae, SiO2, Al2O3. Here, AlSiO. And here if I take, then I take one formula. 3, 2, 1. Now, according to the definition of a system component, it is the minimum number of components or formulas that describe the chemical variability of a system. So, if I take that definition, then this is correct. Because this is the minimum number of components that describes the chemical variability of the phase. But, so, Al2SiO5 can be described only by one formula. That is Al2SiO5 only. So, it is a one component system. One component system. Phase, if you ask me phase, I said you told me a formula. Now you are asking me phase. You tell me the phase. You ask me a formula, I am telling you this is the phase component. This is one. Which phase, how many phase? That you tell me. So say for example, if you have the Al2SiO5 pressure temperature condition and you have this, so you know this is sedimenite, this is andalusite, this is kyanite. All of them have the same formula, Al2SiO5. Now, whether it's kyanite, whether it's only sillimanite, L2SiO5 will have one phase component. If it's only kyanite, it will have one system component. If it's andalusite, it will have one phase component. If it is andalusite and sillimanite, that means you are lying on this line, andalusite and sillimanite together along this line, it's still one component. If you have kyanite, sillimanite, it's still one component. If you are here, where andalusite, sillimanite and kyanite, all three should be in equilibrium. All three should be in equilibrium. The component is still one. Right? That's a very, very important point that I want to make. So this is what is important about system components. Say, for example, just this, and after that we will. Now you see how this changes. Say, you know, if you work in low-grade metamorphic rocks normally, you see a lot of veining. These are very famous. These are called, don't ask me why they form in a completely different way. There is something called sillimanite quartz veins or kyanite quartz veins. These are veins that intrude the rock. They are not metals because at such low temperatures you don't heat the rocks. They are formed due to some process and we ignore the process. But there could be a rock where you have sillimanite and quartz. So you know whether it is sillimanite or kyanite, it does not matter. Let's say the formula is Al2SiO5. Let's say the formula is Al2SiO5. It's an aluminosilicate. And you have quartz. So now you have a two-phase system. Could be three. If both sillimanite kyanite is there, if sillimanite kyanite and andalusite also is there, then it's a four-phase field. But whatever it is, it has an aluminosilicate and it has a quartz. Now what will be our phase component? This is Al2SiO5 and this is SiO2. Quartz is SiO2. So how many phase components? We can do it by writing, you see, I can write in terms of Al, Si and O. I can write like before, 2 Al, 1 Si, 5 O, and this one, 1 Si and 2 O. So I can take this, or I can write Al2O3 and in terms of Al2O3 and SiO2. So this will be 1 Al2O3 plus 1 SiO2, right? And this will be 0 Al2O3 plus 1 SiO2. So this could be another possibility. Here there are 3 components, here there are 2 components. But if I take Al2SiO5, then I can write this as 1 Al2SiO5, but I don't have anything for SiO2. I don't have anything for SiO2. So here the best is, this is out of question. We are left with AlSiO, 3 system components, or Al2O3 SiO2, 2 system components. And you would say minimum number of components. So it's a 2-component system. So this is acceptable. Not this, because it's too many. And this, because it's too less. This is correct. Al2O3 and SiO2. Now just before we conclude, I can just tell you this. I could, instead of taking this, I could have also taken Al2O3 and Al2SiO5. Sounds strange, huh? But no, it's right. Thermodynamically perfect. Thermodynamics does not understand these ones. It understands numbers. Al2O3, Al2SiO5. Then you will see, what's happening? Very simple. Al2SiO5, how will you write? As 0 Al2O3 plus 1 Al2SiO5. And you have SiO2, you will write as minus 1 Al2O3 plus 1 L2SiO5. Done with? Yes, it's right. So here also 2 components. This is equally valid. Also equally valid is SiO2 L2SiO5. Equally valid. So all these 3, 1, 2, and 3, all are correct. So long the number is 2. Rest, it doesn't matter. You can have L2O3 SiO2, you can have L2O3 L2SiO5, you can have SiO2 L2SiO5. Doesn't matter. But you can't have AlSiO, 3 component, it is wrong. And you can't take L2SiO5 because you can't describe the formula of SiO2. So essentially, if you take this, you see, if you take this is the composition of this one, and this is the composition of quartz. So it's a 2-component system. Phase, that depends on what is there. So long its formula is L2SiO5. So long its formula is SiO2O5. Okay, I think I will stop now. Yeah.